What if you could make the properties of the material repeat as you move through time? Imagine you're standing in front of a window. The window is clear, then dark, then clear, then dark, then clear again, and it keeps doing this over and over. But now imagine that happening trillions of times faster than you could possibly see. That's roughly the idea behind a photonic time crystal. The material's ability to interact with electromagnetic waves changes in a repeating rhythm through time. And scientists have now experimentally demonstrated an all-optical version of one. The researchers created a special artificial material called a plasmonic metamaterial. It contains microscopic structures made from gold combined with a semiconductor. Then they blasted it with powerful terahertz electromagnetic waves. Terahertz radiation sits between microwaves and infrared light on the electromagnetic spectrum. And something remarkable happened. The intense electromagnetic field changed the behavior of electrons inside the material. That changed the material's optical properties. But it didn't simply change them once. The properties changed, then changed again in an incredibly fast repeating rhythm. The changes happened on the scale of picoseconds. A picosecond is just 1/1,000,000th of a second. That repeating pattern in time created the photonic time crystal. But here's the important question. Why would we want to do this? Because it gives scientists a completely new way to manipulate electromagnetic waves. Imagine a child sitting on a swing. If you give the swing one push, it moves for a while and eventually slows down. But suppose every time the child swings toward you, you give another perfectly timed push. Push, swing, push, swing, push, swing. Each perfectly timed push adds more energy. Eventually, the child swings higher and higher. Something conceptually similar can happen inside a photonic time crystal. If you change the material's properties at precisely the right rhythm, energy from that changing material can be transferred into an electromagnetic wave. Instead of the signal simply losing energy as it travels, you can potentially amplify it. And the researchers are already seeing signs of this effect. In this experiment, the time crystal behavior reduced the losses of one optical mode by more than 50%. That's important because normally electromagnetic signals lose energy. But imagine engineering a material that actively fights against that loss. And if scientists can eventually make the amplification stronger than the remaining losses, something even more interesting could happen. The photonic time crystal could become a laser, and not necessarily a laser like the little red pointer you've seen before. Researchers are particularly interested in producing new kinds of terahertz lasers. Terahertz radiation occupies an unusual part of the electromagnetic spectrum between traditional electronics and infrared light, and we're still learning how to use it effectively. Controlling terahertz radiation could eventually be useful for things like medical and scientific imaging. Many molecules interact with terahertz frequencies in distinctive ways, meaning terahertz technology could potentially help us examine materials and biological systems without using damaging ionizing radiation. But that's only one possibility. There's another potentially enormous application: communications. Most wireless technology today operates at much lower frequencies. Future communication systems could increasingly use extremely high-frequency electromagnetic waves to carry enormous amounts of information. Photonic time crystals might eventually help manipulate and amplify those signals extremely quickly. That could contribute to future generations of wireless communication and extremely high-speed data transmission. And then there's computing. Modern computers manipulate electrical signals incredibly quickly, but photons can also carry information. If scientists can control light almost instantaneously by changing a material's properties on picosecond timescales, photonic time crystals could eventually become components in ultra-fast optical or photonic computers. Instead of controlling electrons with electronic circuits, we could increasingly control photons with light. And there may be applications we haven't even imagined yet. Think about what happened when humans first learned how to control electricity. At first, it was simply a strange natural phenomenon. Eventually, it gave us electric motors, radio, television, computers, smartphones, and the internet. Learning new ways to control light could potentially open similar doors. But there's something very important to understand. Scientists have not just invented futuristic optical computers or revolutionary new communication systems. Those are potential future applications. What they demonstrated is the underlying physical effect that could eventually make technologies like those possible. And that's what makes this discovery so exciting. For most of human history, when we wanted to engineer how light behaves, we designed structures in space. Put this material here, put another material there, build a repeating structure. Now we're beginning to engineer the environment experienced by light in another dimension, time. We're learning how to tell photons not only where something should happen, but when. And that could give humanity an entirely new level of control over light.